Welcome to Com Science. Today, we're doing a deep, um, really expansive analysis of maybe the most perplexing visitor to grace our solar system in, well, recent memory. It's the interstellar comet, pronounced 3I Atlas.
Yeah, and this object, came from a completely different star system.
Hmm.
And it's doing something, well, it's pretty extraordinary, actually. It's basically defying every textbook prediction we thought we had about how comets are supposed to behave. We've got this, stack of sources now. There's UV data showing water activity that just seems impossible. Then there's spectroscopic results giving us a chemical composition that really fundamentally challenges our models of how planets even form. And yeah, there are even some, let's say, provocative theories floating around suggesting, maybe technological origins.
Right. So our mission today is to try and synthesize this mountain of conflicting, sometimes really sensationalized information. We want to cut through the noise, look closely at the actual scientific anomalies, and prepare you for this critical period that's happening literally right now, which is the hidden perihelion passage. We're really focusing on getting that definitive, quiet understanding of what this cosmic time capsule is truly telling us about the universe, outside our own solar neighborhood.
Mhm. And the paradox of 3I Atlas is just so stark. It's what makes it such a fascinating thing to study. It's incredibly ancient. We're talking potentially 10 billion years old. That makes it one of the oldest objects we've ever even sampled from outside our local system. It's completely unique, too, in our, well, very small sample set of interstellar visitors so far. And yet it's approaching its most dramatic moment, perihelion, its closest point to the sun, precisely when the geometry, the layout of the solar system means it's completely hidden from Earth. So we're forced into this information blackout that's going to last for months, it almost feels like a bit of cosmic cruelty, denying us the climax of this incredible visit.
Okay, so let's start with that immediate shock, the thing that's been called the fire hose mystery. Back in late July, early August, NASA's Swift Observatory, which mostly looks at X-rays and UV light, it detected this unbelievable amount of activity just pouring off the comet. I want you to just sit with this number for a second because it's really key to understanding the anomaly. 40 kilograms of water being ejected from 3I Atlas every single second.
40 kilos a second. To put that in perspective, that's roughly the mass of a large adult person every 2 seconds, just jetting out into space. And this wasn't happening when it was really close to the sun either. This detection was made when the comet was at 2.9 astronomical units, or AU.
Right. And for anyone maybe not familiar with AU, 1 AU is the distance from Earth to the sun. So 2.9 AU, that's nearly 3 times farther out than we are. It puts the comet firmly out between the orbits of Mars and Jupiter. And at that huge distance where the sunlight is, much, much weaker, water ice should barely be sublimating at all. The energy input is just way too low to drive that kind of intense activity.
And this is where it really starts breaking the rules, the ones established by, decades of looking at comets. Our distance-based predictions for typical solar system comets, they suggest that way out at 2.9 AU, you should only see maybe 3 to 5% of the comet's surface actively releasing gas. That's because most of the surface is usually covered in this, like dusty crust, a mantle that insulates the ice underneath. But 3I Atlas, it showed at least 8% active surface, nearly double the expected activity. It was shining brighter, throwing off vastly more material than its estimated sizing. Nucleus, maybe only 5 to 6 kilometers across, should have possibly allowed.
So the scientific reaction wasn't just, oh, that's surprising. It was more like, wait, what? Why is it so active?
Exactly, because the math just doesn't work. Not for pure surface sublimation anyway. If you take the comet's measured size, let's say 6 kilometers in diameter, and you calculate the solar energy actually hitting that surface way out at 2.9 AU, the energy input is mathematically insufficient. It cannot explain 40 kilograms per second of water just boiling off the surface. Something else had to be going on, something acting as an amplifier, or maybe a secondary source of evaporation.
And this is where other instruments started giving us clues, right? While Swift saw the effect that massive water output near infrared observations started hinting at the cause, instruments like Gemini South down in Chile and NASA's Infrared Telescope Facility, the IRTF in Hawaii, they started catching hints of the answer. It wasn't just vapor escaping. It was actual ice debris, chunks, fragments of water ice floating in the coma itself, not just coming off the surface.
Yes, exactly. That seems to be the key mechanism. Think of it like this, maybe. Imagine trying to melt one single giant ice cube versus shattering that same ice cube into, thousands of tiny pieces and spreading all those pieces out in the sun. The tiny fragments, because they have a vastly higher surface area compared to their volume, they heat up much, much faster than the big, solid nucleus, the 6-kilometer rock. So each of these floating fragments basically becomes a miniature, super efficient steam vent. You get hundreds, maybe thousands of them scattered through the coma, and collectively they contribute to that massive total water output that Swift was seeing. The end result is that the nucleus looks way more active than its solid, dusty surface actually is.
Huh. That's a really neat solution to the anomaly. So it means a comet isn't just, an intact, dirty snowball. It's more like a dirty snowball that's constantly shedding chunks of itself. Precisely. And what's really fascinating here, as astronomer Zexi Xing pointed out, is that every single interstellar comet we've seen so far has been a complete surprise. It forces us to constantly update our models. Remember Oumuamua, the first one? It was basically dry, almost inert, acted more like an asteroid. Then Borisov, the second one, turned out to be really rich in carbon monoxide. And now 3I Atlas is just, well, hemorrhaging water at a distance where we absolutely did not expect it. These visitors, they're collectively rewriting the comet science textbooks one by one. They're showing us just how incredibly diverse objects born in other star systems might be.
Which then leads us to the really critical, sincere question. Why are those ice chunks even there in the first place? They shouldn't just be floating off so easily, so far from the sun, unless they were somehow liberated fairly recently. And there seem to be a couple of main theories for where they came from. Right. The first one involves internal stress. Maybe there was some kind of relatively recent fragmentation event, or an outburst that happened before we even spotted the comet, like perhaps a pocket of volatile gas, maybe CO2, exploded just beneath the surface and launched all this debris out into space. The second theory, which is maybe a bit more poetic, it connects back to its incredible age. Is this debris something that's just accumulated over millions, maybe billions of years from constant low-level impacts by micrometeorites during its, estimated 10 billion year journey through interstellar space?
Wow. So if that second one is true, if its surface has just been slowly eroding away in the vacuum of deep space for billions of years, then this icy debris field isn't temporary. It's just a permanent feature of its structure, reflecting how old it is.
And that ties directly into the most profound idea, which links to where it might have originally come from. This icy debris field might actually reflect a fundamentally different structure for comets that originated way back in the thick disk of the galaxy that's the oldest population of stars. Maybe this structure, where volatile pockets are easily exposed and shed, is just how ancient comets behave. Fundamentally different because they formed under conditions our own solar system never experienced. Maybe they have a less coherent, more porous internal structure naturally.
Okay, so we've established the water fire hose anomaly seems to be explained by this icy debris field. But that debris itself only leads us to the next, maybe much deeper mystery, the comet's actual chemical makeup. If the amount of water was a surprise, the compositional data we got from the James Webb Space Telescope, JWST, well, that was a true revelation, like getting a core sample from deep time.
Yeah, JWST looked at 3I Atlas back on August 6th. It was slightly farther out then, around 3.32 AU. Still distant, still cold. But this gave JWST's instruments the perfect chance to chemically analyze the faint gases escaping from the nucleus. Specifically, the NR-SPEC instrument, that's the near-infrared spectrograph. It captured the comet's chemical fingerprint.
We should probably pause here and explain what NR-SPEC actually does. It's not just taking a picture, right? It's capturing a spectrum of light in the near-infrared range. It basically gives you a highly detailed chemical barcode. Different molecules absorb and emit light at very specific wavelengths, like a unique fingerprint for each one. And that's what lets astronomers tell the difference between, say, water vapor and methane or carbon dioxide, even when they're millions and millions of miles away.
Exactly. And that chemical barcode, it revealed a massive outlier. The instrument measured a ratio of about 7.6 to 1. Some analyses rounded up to 8 to 1 of carbon dioxide CO2 to water H2O. Now, this isn't just slightly odd. This is fundamentally different from what we typically see in comets from our own solar system.
Let's try and put that number 7.6 to 1 into context for you listening. Typical solar system comets, especially the ones coming from the Oort cloud way out past Neptune, they're usually closer to 1-to-1 CO2 to water. Or often, they're heavily water-dominated. Water is typically the main gas we detect coming off them. This ratio, 7.6 CO2 for every 1 water molecule, is quantified as being 4.5 sigma above the expected trend line.
Yeah, and that statistical deviation, the 4.5 sigma, that's the real story here. To put 4.5 sigma in perspective, it means the chances of this ratio just occurring naturally, randomly, under the known physical and chemical conditions that created our solar system is less than 1 in a million. This isn't just an outlier. This is a fundamental deviation from the planetary formation physics we thought we understood. It's forcing us to consider some truly extreme conditions for where this thing came from.
Okay, let's unpack those extreme conditions. The data seems to lead to two main hypotheses. They're kind of mutually exclusive, but both are equally challenging, really, about the comet's 10 billion year history. Hypothesis 1 involves extreme radiation processing.
Right. So the idea here is if 3I Atlas spent 10 billion years wandering through the harsh environment of the galaxy, not protected way out in an Oort cloud like our comets, but constantly being bombarded by cosmic rays, high-energy particles, those rays could have preferentially destroyed the molecules that are chemically weaker over time. Water molecules, H2O, are actually easier to break apart chemically than carbon dioxide, CO2.
Wait, hang on. If this had spent 10 billion years getting bombarded, wouldn't that radiation eventually break down all the volatiles? Why would the CO2 survive better? Is the chemical bond just that much stronger?
It is significantly stronger, yes. Water has a relatively low dissociation energy threshold. It doesn't take as much energy to break it apart. So over billions and billions of years, the cumulative effect of all that cosmic ray bombardment, it's called radiolysis, it would gradually strip away the hydrogen and oxygen from the water ice. But the CO2 molecule, with its tighter double bonds, it's just much more robust. It holds together better. So an initially water-rich comet could become progressively more carbon dioxide-rich through this process of attrition, just wearing down the water over immense timescales. It's less about perfect survival, more about which molecule is statistically harder to destroy over 10 billion years.
Okay, that makes sense. But it requires the water ice to have been constantly exposed or maybe shielded in just the right way, that the processing still accumulated to that extreme degree. But the second implication, which feels maybe even more radical, is about where it actually formed in the first place.
It's exactly. Implication 2 suggests that maybe 3I Atlas formed way out beyond the CO2 ice line in its parent star's protoplanetary disk. For those who need a quick refresher, the ice line, or snow line, is just the distance from a young star where a specific volatile compound gets cold enough to freeze solid into ice. Water freezes relatively close to the star. CO2 freezes much farther out, where it's colder. So if this comet formed way out beyond that CO2 ice line, it would have been born in a region where carbon was maybe unusually abundant compared to oxygen, and it would have frozen in that roughly 8-to-1 CO2 to water ratio right from day one, just based on the available material.
Okay, but that scenario demands really specific, maybe atypical conditions, right? It suggests a parent protoplanetary disk that looked noticeably different from the one that formed our Earth and Jupiter. It suggests a star system that was maybe just carbon-rich from the get-go, or perhaps had a different metallicity, or a much different temperature profile during its formation period billions of years ago.
And interestingly, the structural observations that JWST gathered actually seem to support this idea of a, well, heterogeneous makeup, a mixed bag. The data showed that the water emission wasn't smooth. It was highly localized, kind of patchy. It suggests discrete jets or pockets of water-rich ice mixed into the overall matrix. It wasn't uniform across the surface.
But conversely, the CO2 emission looked much smoother, more widespread.
Exactly. Consistent with sublimation happening pretty much across the vast majority of the sunward hemisphere. This suggests that the bulk structure, the main body of the comet, is probably CO2 ice, acting as the main widespread matrix. And the water exists only in these discrete, isolated chunks or layers embedded within it. In this kind of extreme heterogeneity, this lumpiness, it naturally fuels that icy debris field theory we talked about earlier. Those water pockets, being maybe less structurally sound or just different, are the parts most easily broken off and shed into the coma.
Okay, so this connects right back to the origin story then.
Right. If we lean into the hypothesis that 3I Atlas came from the galactic thick disk, those stars that formed up to 10 billion years ago, long before our sun even existed, then this extreme age and this unique composition strongly suggest the comet is a true physical artifact from that ancient epoch. We're not just looking at a computer simulation of early galactic chemistry anymore. We are looking at the actual material from back then.
And that specific composition, being so CO2 rich, has potentially enormous implications for, well, the habitability of ancient star systems. A parent star system that's rich in CO2 and likely sulfur, because we also have some tentative detections of carbonyl sulfide OCS, but potentially poor and accessible water. That raises some major questions about what life might look like, or if it could even arise in such an ancient, chemically different environment.
Exactly. If this CO2-rich composition turns out to be typical of the galactic thick disk, the oldest population of stars in the Milky Way, it could mean that the majority of ancient exoplanetary systems might operate on fundamentally different chemistry than we assume based on our own system. Right now, we're mostly looking for Earth-like oxidized water worlds because we assume H2O dominance based on our local example. But maybe the universe, or at least the ancient universe, was actually dominated by these CO2-rich, maybe reduced compound worlds. This single comet, this little 5-kilometer chunk of ancient ice, is potentially upending some of the basic assumptions we make in the search for extraterrestrial life. It's showing us that the chemistry of life elsewhere might be far more alien than we currently imagine. #tag3, the hidden passage in the critical. Wait.
Okay, so now we arrive at the present moment. This is the reason why the scientific community is kind of holding its collective breath, even as we're recording this. We've talked about the secrets the comet carries. Now we need to address the immense danger it faces right now. The geometry of its path is, as you said earlier, almost cruel.
Yeah, 3I Atlas is currently deep in solar conjunction. That means it's passing almost directly behind the sun from our perspective here on Earth. It reached perihelion, its closest approach to the sun, back on October 29th. It got down to about 1.36 AU, which is just inside the orbit of Mars. But right now, it's completely hidden from Earth's view, only about 12 degrees away from the sun in the sky. No ground-based telescope, no Earth-orbiting telescope can safely or effectively track it during this crucial period, which lasts for roughly 3 months in total.
So we're forced to just consider the physics of what's happening, unseen. We know that 40 kilograms per second of water was the baseline activity way out at nearly 3 AU. The solar flux, just the sheer intensity of the sun's energy at 1.36 AU, is orders of magnitude stronger, much, much more intense. This is subjecting the comet, which we now know is dominated by this low-temperature dry ice CO2, to immense thermal stress.
Think about the sublimation temperatures involved. Water ice turns to gas, sublimates, around 200 Kelvin, which is about minus 73 Celsius. CO2 ice sublimates at about 195 Kelvin, or minus 78 Celsius. That difference seems small, maybe, but the rate of heating at 1.36 AU is incredibly intense compared to what it experienced farther out. The textbook answer is pretty straightforward. The dry ice should just explode with activity. The coma, the gas cloud around it, should expand dramatically. And the internal pressure from all that sublimating CO2 could become overwhelming. But, as we've seen, 3I Atlas hasn't exactly followed the textbook so far. So the central question of this whole deep dive really becomes, is it tough enough to survive this solar oven that's currently passing through?
And the only observers who are getting any kind of view right now are our robotic spacecraft, positioned elsewhere in the solar system. And we did get one incredibly critical, though brief, glimpse when Mars witnessed the visitor back on October 3rd. The comet swept past Mars at a relatively close distance, about 29 million kilometers.
Yes, that was crucial. ESA's Trace Gas Orbiter, TGO, and NASA's orbiters around Mars were all watching closely. TGO's images confirmed the comet was still intact, which was a big relief because some models had predicted it might start breaking up even before perihelion. It also confirmed it was following its predicted orbital path precisely, and it was still highly active. So far, so good, mostly. But there was a subtle clue captured by TGO that kind of speaks directly to the uncertainty we're facing during this current blackout period.
Oh, what was the subtle clue?
The coma, the diffuses envelope of gas and dust surrounding the nucleus, it looked slightly larger than expected. Standard models, based on the activity seen way out at 3 AU, predicted a coma size maybe around 2,000 to 3,000 kilometers across. But the TGO images suggested the coma was actually closer to 4,000 or maybe even 5,000 kilometers across. Now, it's an ambiguous observation. It could simply mean the comet was slightly more active than predicted as it got closer to the sun, which is normal. Or it could mean that the contribution from that icy debris field we talked about had increased dramatically as it moved into warmer regions. More chunks breaking off, maybe. It was just a faint but slightly unsettling hint that the physics were maybe accelerating faster than we thought.
And that feeds directly into the big fragmentation question, doesn't it? Which is the really high-stakes consequence of this hidden passage. The history of comets reminds us that the risk of breaking up is terribly real. We all remember comet Shoemaker-Levy 9 shattering into pieces as it approached Jupiter back in the 90s. And even the comet this one is sort of named after, the short-period comet Atlas C 2019Y4, that one disintegrated pretty violently back in 2020 as it approached the sun.
Yeah, and the mechanism of destruction here is critical to understand. It's not just about the external heat baking the surface. It's the combination of that external thermal shock hitting the cold nucleus and that immense internal pressure building up from the sublimating CO2. When the sun heats the surface layers, the CO2 ice underneath turns rapidly into gas, building up pressure like a giant cosmic soda bottle being shaken. If that pressure becomes strong enough to suddenly blow away the insulating dust layer on the surface, the whole nucleus can suffer a catastrophic structural failure and just tear itself apart.
So we're left with this really high-stakes dichotomy, this fork in the road during the blackout. Will 3I Atlas somehow survive intact? Will it emerge from behind the sun as that single, coherent time capsule, preserving the layered 10-billion-year-old chemistry of its parent star system? Or will it succumb to the heat and the pressure, shattering into multiple pieces? Which, might offer us fragmented samples of its interior layers. Maybe that's interesting too. But it would deny us that single, coherent core sample we really crave.
And this brings us to the truly frustrating, yet absolutely essential element of this whole investigation, what we're calling the data latency. While the comet is hidden from Earth right now, we are basically pinning our hopes on one specific space asset to give us the definitive answer about its survival. ESA's JWST spacecraft, that's the Jupiter Icy Moons Explorer.
Ah, right. JWST is heading out towards Jupiter, so its vantage point is different. It's perfectly positioned to get post-perihelion observations, isn't it? Between about November 2nd and November 25th, right as 3I Atlas emerges from behind the sun and starts heading back out. Because JWST is way out there, traveling deep into the solar system, its viewpoint should give us the essential structural and compositional data about the immediate aftermath of perihelion. Did it survive? What does it look like now?
Exactly. And JWST is carrying the perfect instrument suite for this job. It's got the JANUS camera for visible imaging to see the structure. It has the MEJIS spectrometer to study the surface and atmosphere composition. It has the UVS ultraviolet spectrometer and the PEP, the particle environment package, to measure the gases and ionized particles in the coma. This suite of instruments can absolutely tell us if the nucleus survived the passage and what its composition looks like after that intense solar baking.
Okay, so the data will exist sometime in November. That's the good news. But here's the cosmic punchline, the frustrating part.
Yeah. Due to current operational constraints, JWST is using its medium-gain antenna, not its big high-speed dish right now, partly using it as a heat shield during this phase of its journey. This means data transmission back to Earth is slow, agonizingly slow.
So those critical, potentially high-resolution November observations, they won't be fully downlinked, processed, and actually released to the scientific community until February 2026.
That's the current estimate, yes, February 2026. That's effectively a 3-month blackout period after the observations are taken, waiting for the definitive answer regarding its survival. We'll know the answer exists right now, captured in photons recorded on a spacecraft way out near Jupiter, but we won't be able to access it for months. It requires immense scientific patience.
Okay. So while the mainstream scientific community is, waiting with that immense patience for the critical JWST data in February 2026, there is this alternative narrative, one that has definitely captured the public imagination and, well, it demands impartial discussion. And that is the mothership hypothesis, which has been primarily put forth by Harvard physicist Avi Loeb.
Right. Loeb's proposal basically suggests that all these accumulating statistical outliers, we've just spent time detailing the unusual activity way out at distance, the extreme chemical composition. He argues that these warrant a shift in how we assess the object. He suggests we have to seriously consider the non-zero probability that this isn't just a comet, but maybe an artificial technological artifact, perhaps a reconnaissance craft from another civilization. He suggests moving the object on his own classification scale from maybe a 4, which means likely natural, up to a 6, meaning potentially technological.
And the core of his case seems to rest pretty heavily on statistical anomalies that go beyond just the composition. First, there's the trajectory itself, which he calls anomalous. Loeb's team calculated what they say are vanishingly small odds, 0.005%, or 5 chances in 100,000 that a randomly entering interstellar object would just happen to pass as close as 3I Atlas does to not just one, but 3 major inner solar system bodies, Venus, Mars, and Jupiter.
Yeah, he argues that such a highly optimized flyby trajectory suggests maybe it wasn't a random entry at all, but perhaps a guided entry, specifically aimed at gathering the maximum amount of information from our solar system in one pass. I mean, if you were designing a reconnaissance craft from another system, this path does give you the most, observational bang for your buck, statistically speaking.
Yeah.
Fly by multiple interesting targets.
Then there's the timing of perihelion, its closest approach to the sun. He notes that October 29th, the date it happened, is the mathematically optimal location for a propulsive maneuver, something scientists call the O-birth effect.
All right, we should probably define the O-birth effect here. It's essentially taking advantage of gravity assist. It's the point in an orbit, usually closest approach to the massive body, perihelion in this case, where the object is already moving fastest relative to the sun. So if an engineered craft wanted to maximize the efficiency of firing its engines, say, to slow down slightly and maybe enter a capture orbit around the sun or deploy something, that specific point, perihelion, is mathematically the best moment to apply thrust to change its orbital path most effectively with the least amount of fuel.
And building on that idea, he suggests this perihelion timing would be the perfect moment for a hypothetical mothership to deploy small, maybe 10-kilogram reconnaissance probes. This is what he calls the dandelion hypothesis, like seed scattering, using a sort of reverse Oberth maneuver to gently slow these smaller components down and maybe nudge them into Earth orbit.
And based on these theoretical physics calculations, Loeb calculated an arrival window for these hypothetical probes into Earth orbit. He estimated it would be late November, specifically somewhere between November 21st and December 5th of this year. This is precisely why his private initiative, the Galileo Project, has observatories currently monitoring the skies during that specific window. They're looking for exactly this scenario: objects moving in non-ballistic trajectories. Objects that appear to be steering or slowing down unnaturally, not just following gravity.
Okay, so that's the hypothesis, laid out as impartially as we can. Now let's turn to the immense pushback from the scientific establishment, because they are pushing back hard against this interpretation. Tom Statler, who's NASA's lead program scientist for small solar system bodies, stated it pretty bluntly. He said 3I Atlas very, very strongly resembles the comets that we know. The overwhelming scientific consensus is that this is a natural, albeit very unusual, comet.
Yeah, and the scientific community systematically dismantles the anomalies that Loeb relies upon for his case. They often explain them through conventional, even if somewhat rare, physical processes, or sometimes just through historical observational errors that got refined over time. For example, that early size discrepancy. The initial claims that it looked huge, maybe 20 kilometers across, that was almost certainly just due to observational uncertainty when the comet was extremely faint and far away. Later, as it got closer and brighter, higher resolution observations from multiple sources converged on the much more normal 5 to 6 kilometer nucleus size. That's just standard refinement, not an anomaly.
Right. And similarly, the early spectroscopic confusion, those initial reports that were missing signatures for certain expected gases, that was likely due to a low signal-to-noise ratio when the comet was still very distant and faint. Later, the powerful JWST confirmed the presence of all the expected standard cometary volatiles: water, CO2, even sulfur compounds like OCS. They're just present in very unexpected proportions. The chemistry is unique, yes, but the ingredients are standard cometary material.
But the core test, really, the most damning rebuttal against the technological claim, comes down to two things: heat and movement. First, heat. If it were a technological artifact with active propulsion, or even just passively regulating its internal systems or deploying probes, it should generate waste heat, some excess thermal energy above and beyond what the sun provides. But there is absolutely no excess thermal emission detected by JWST or the Spherix telescope. The heat signature is perfectly consistent with just a cold, icy body being passively warmed by the sun. No internal heat source detected.
And second, the movement. Most crucially, its trajectory. Despite that perihelion timing being theoretically optimal for a supposed Oberth maneuver, the comet adheres perfectly to predictable Newtonian mechanics. It is following its gravitational trajectory precisely as expected. There have been no observed burns, no course corrections, no unexplained changes in its path whatsoever. If it were accelerating or decelerating non-gravitationally, even slightly, our tracking systems would see it immediately in the positional data. And they haven't.
So this just brings us back to that fundamental scientific principle. Extraordinary claims require extraordinary evidence. And the actual evidence accumulated so far, the thermal profile, the lack of any observed thrust, the presence of standard, albeit unusually mixed, cometary volatiles, it all points overwhelmingly towards a natural object. A highly unusual comet, yes, almost certainly one that formed under unique physical conditions, perhaps 10 billion years ago in a different part of the galaxy, but a natural comet nonetheless.
But the hypothesis still resonates, doesn't it? Deeply with the public. And we've seen social media just go absolutely wild during this period of blackout and speculation.
Oh, absolutely. It taps into that very human desire for significance, for contact, for answers to the big questions. We saw the immediate flood of misinformation online. There were TikTok claims predicting an imminent collision, which was never a possibility. There were fringe religious interpretations popping up. There was even that bizarre claim trying to link the temporary U.S. government shutdown back in October to a deliberate cover-up, supposedly to prevent the release of detailed images from the Mars flyby. It's just the nature of information or misinformation in the modern era, isn't it? People retrofitting intent and conspiracy onto random events and statistical outliers.
Yeah. And the ultimate impact of all this constant, often baseless, sensational speculation is, well, it's that the real, complex, genuinely fascinating science of this 10-billion-year-old thick disk comet gets buried. Its truly weird CO2 anomaly, its potential structural secrets, what it tells us about deep-time galactic chemistry. All that subtle, difficult science gets lost under narratives that require basically no evidence to propagate online. We risk losing the subtle wonder in favor of the instant, easy spectacle. Hashtag tag outro.
So as we kind of conclude this deep dive, let's just quickly synthesize the true learnings, the things we have reliably extracted from the actual data, independent of all the speculation and the noise. First, 3I Atlas is chemically dominated by carbon dioxide, maybe by a ratio of 7.6 or 8 to 1 over water. This extreme ratio is telling us it's a messenger, a sample, from a star system with profoundly different formation conditions than our own.
Second, it's almost certainly an ancient object, likely originating from the galactic thick disk, potentially dating back 10 billion years, which means the knowledge it carries about early galaxy chemistry, about carbon abundance versus water in ancient systems, that knowledge is truly irreplaceable.
And finally, its structure appears to be anomalous. Its massive water activity, especially at distance, seems to be amplified by this floating field of icy debris shed from the nucleus. It's breaking all the textbook rules we thought we had about cometary activity, especially far from the sun. It's teaching us that a comet's surface isn't just a simple uniform insulator, but maybe a much more dynamic shedding system, even way out in the cold.
The stakes for understanding this object are incredibly high. We know we will gain critical post-perihelion data from the JWST spacecraft's observations in November. That will give us our only definitive view of the comet's structural integrity after its intense solar baking. Did it hold together? But we must wait, with immense scientific patience, as that definitive data won't be fully processed and released until February 2026. And this is our only chance to study this unique visitor up close because it's already leaving the inner solar system. It'll pass beyond Jupiter's orbit sometime in March 2026, heading back out into interstellar space forever.
We know 3I Atlas is an ancient time capsule. It has cruised silently past thousands, maybe millions of other star systems during its incredible 10-billion-year journey across the galaxy to reach us. As we wait for that crucial data in February 2026 to finally see if it survived its current hidden passage behind the sun, this raises a final question for you to carry with you.
Is it possible that this object, maybe the oldest physical sample we have ever encountered from the wider galaxy, is not just carrying secrets about planetary formation, but is itself a silent witness, a representative of a time and a place in galactic history we can no longer directly reach, regardless of whether its current, strange activity turns out to be entirely natural, or something else that simply requires us to rewrite our textbooks entirely?